Hello everyone, welcome to session number 24 of Java programming. In today's lecture, we will discuss multi-threading case studies in Java. Through real-world examples, we will understand how multi-threading concepts are applied in practical scenarios. In the previous lecture, we studied thread synchronization techniques and inter-thread communication. We learned how synchronization prevents race conditions and how threads communicate using wait, notify, and notify all methods. Why do we use multiple threads instead of a single thread? Why we see multi-threading in daily life, such as downloading files, online gaming, and user interface applications. If synchronization is not used properly, data inconsistency, race conditions, and unpredictable behavior may occur. At the end of this session, you will be able to analyze real-world scenarios that apply multi-threading concepts in Java. You will also be able to develop and evaluate multi-threaded Java programs that demonstrate safe and efficient concurrent execution using case studies. In this session, we will study multiple case studies related to multi-threading, including producer-consumer problems, banking transactions, thread pools, file downloading, and synchronized bank accounts. A case study is an in-depth examination of a real-world problem or scenario. It focuses on real-life context, detailed analysis, and learning how theory applies in practice. In computer science, case studies help us understand how concepts like multithreading solve practical problems. For example, a case study on multithreading in Java banking applications examines how multiple transactions occur simultaneously, what challenges arise, and how synchronization prevents data inconsistency. In the producer-consumer problem, two threads share a common buffer. The producer generates data and the consumer uses that data. Both threads must coordinate their execution to avoid errors. In real-world systems, producers generate data and consumers process it. If both access the shared buffer simultaneously, data inconsistency may occur. The producer must wait if the buffer is full, and the consumer must wait if the buffer is empty. The solution uses synchronized methods along with wait and notify. This ensures proper coordination between producer and consumer threads and prevents race conditions. The output shows that data is produced and consumed in proper order. The shared buffer class uses a Boolean flag to track availability. The producer waits if data is already available, and the consumer waits if no data is available. Notify is used to wake up the waiting thread after producing or consuming. Modify the producer consumer program to produce and consume 10 items. Observe where wait and notify are essential. Also observe what happens when synchronization is removed from the program. The wait method temporarily releases the lock and makes a thread wait until the notify method is called. The producer waits when the item has not yet been consumed. The consumer waits when no item has been produced. The notify method wakes up one waiting thread so that it can continue execution. If synchronize, wait, and notify are removed, data inconsistency occurs. Race conditions appear where the consumer may try to consume before the producer produces. The output becomes unpredictable and the program may crash due to illegal monitor state exceptions. In this case study, multiple threads represent users withdrawing money from the same bank account. The withdraw method is synchronized to ensure only one thread accesses the balance at a time. If synchronization is removed, multiple users may withdraw money simultaneously, leading to incorrect balances. Thread priorities can influence execution order, but they cannot replace synchronization. Instead of creating a new thread for every task, a thread pool reuses a fixed number of threads. This improves performance and reduces overhead. Executor service manages the thread pool efficiently. In this activity, predict how many threads will run simultaneously. Change the pool size and observe how execution behavior changes. Large files take a long time to download sequentially. A multi-threaded download manager splits the file into parts, and multiple threads download different parts simultaneously. Each file downloader thread downloads a specific part of the file. Threads run concurrently, reducing overall download time. The output shows that parts finish downloading in an unpredictable order. In this case study, multiple users try to withdraw money from the same account. Without synchronization, over-withdrawal may occur, resulting in a negative balance. The withdraw method is synchronized, so only one thread accesses the balance at a time. This prevents data inconsistency and ensures correct balance updates. The output shows that one user successfully withdraws money and the second user is denied due to insufficient balance. This confirms that synchronization is working correctly. To summarize, we studied real-world multi-threading case studies in Java. We discussed thread creation, thread lifecycle, synchronization, inter-thread communication, thread pools, and practical applications like banking and file downloading. In the next session, we will begin the JDBC API, including JDBC architecture and types of JDBC drivers. Now we will be solving a case-based scenario programming problem. So the statement is, uh, problem is, a banking application performs concurrent deposit, withdrawal, interest calculation, and transaction logging. Design a multi-threaded Java solution for the above scenario. B part, evaluate the choice of synchronization mechanisms used. Critically analyze how deadlock, starvation, and race conditions can be prevented. So again, we will be using the IntelliJ IDEA integrated development environment to solve this write this multi-threaded Java solution for this scenario. So as usual, we will hover our mouse to File menu, then we go to New Menu Item, then we click on Menu, we click on New Project, and I have already created a project with the name Multi-Threading Case Study. Let me hide the project folder structure. So design requirements are concurrent operations are deposit, withdrawal, interest calculation, and transaction logging, and the shared resource is the bank account. We need to ensure thread safety, data consistency, efficient concurrency. This program simulates a banking application where multiple operations such as deposit, withdrawal, interest calculation, and transaction logging run concurrently. To ensure thread safety and fairness, it uses reentrant log, condition, and a thread pool. So line number 1 and 2 are import java.util.concurrent.star semicolon, import java.util.concurrent.log.star semicolon. So the first import statement is used for thread pools and concurrency utilities. Second import statement is used for advanced locking mechanisms. Now we go to line number 4 where we are having the class bank account. It represents a shared bank account. This bank account accessed concurrently by multiple threads. Then we go to line number 5, private double balance. It is a shared variable, critical section, also a critical section resource. Then we are having line number 6, private final lock is equal to new reentrant lock, and we pass true as the parameter. So reentrant lock ensures mutual exclusion. It true enables fair locking, prevents starvation. Then line number 7, private final condition sufficient funds equal to log.new condition. So condition object for thread, it is a condition, it represents a condition object for thread communication, and it is used when balance is insufficient. Then we are having the uh, line number 9, public bank account and balance as a parameter of double data type. This dot balance equal to balance. It initializes account balance. Then we are having a deposit method at line number 13, public void deposit, double amount. This deposit method is not synchronized using the synchronized keyword. It is controlled using explicit log. Then we come to line number 20, log.log. This statement acquires the log and blocks other threads. Then we go to line number, sorry. Line number 14 is log.log, line number 14. And this acquires the log and blocks other threads. Then we go to line number 16, balance plus equal to amount. Line number 16, it safely updates shared balance. Then we go to line number 17, system.out.println deposited plus amount plus balance. It logs the deposit transaction. Then we go to line number 18, sufficient funds dot signal all. So it wakes all waiting withdrawal threads and it also prevents starvation. Then we go to line number 19, finally block, log.unlock. It ensures lock is always released. Then we are having a withdraw method at line number 24. Public void withdraw amount as a parameter of double data type throws interrupted exception. So withdrawal may block, it can lead to, if the withdrawal may block, it will throw an exception. Then we are having line number 25, log.log. It, this statement is again used to acquiring the log. Then we are having a while loop at line number uh, while balance less than amount, sufficient funds dot await, line number 28. So if insufficient balance is there, the thread waits and the lock is released while it handles spurious wake-ups. Then we are having line number 30, balance minus equal to amount. So it represents a safe deduction. Then line number 31, system.out.println withdrawn plus amount plus balance. So it logs withdrawal. Then we are having the finally block, line number 32, log.unlock. So it again releases the log. Interest, then we are having the interest calculation method, line number 37. So it adds interest safely. Then line number 38, log.log. It prevents interference with other operations. Then line number 40, balance plus equal to balance into 0.05. So it applies 5% interest. Then line number 41, system.out.println interest added balance colon plus balance. So it logs the interest update. Then we are having finally log line number 42, log.unlock. So then we move to the transaction logger class at line number 47. So class transaction logger implements runnable. So this statement is used to separate the logging task. It also demonstrates non-blocking parallel work. Then we are having a run method at line number 48 and system.out.println transaction logged by plus thread.current thread.get name. So this code runs independently, does not it this these two statements does not access shared balance. Then we are having the main class at line number 52 because main method resides within this main class. And this main class represents a driver class. Then line number 54, bank account is equal to new bank account 1000 as a parameter. So this statement creates shared bank account. Then we are having line number 56, executor service executor equal to executors dot new fixed thread pool 4 as a parameter. Line number 56. So this statement represents a thread pool with 4 threads and it controls concurrency efficiently. Then it also used for submitting the task. Then we are having the line number 58, executor dot execute arrow operator account dot deposit 500 as a parameter. So this represents a deposit task. Then we are having line number 59. Line number 59 is executor dot execute arrow operator account dot deposit again 500. No, we now move to line number 59. Executor dot execute. Then we are having a try block at line number 60. Account dot withdraw 1200 as a parameter. And then we are having a catch statement interrupted exception E. So this piece of code represents the withdrawal task and uh, withdrawal may wait due to insufficient funds. Then we are having line number 64, executor.execute account calculate interest. So it represents interest calculation task. Then we are having line number 65, executor dot execute new transaction logger, line number 65. So it represents a logging task. And then we are having last statement, executor dot shutdown. That is a shutdown executor. It stops accepting new tasks and allows running tasks to complete. So what is the summary of this program? Let me execute this program by pressing this green button and we can see the output. Build process is running. So as we can see here, this is the output of the program. So what is the summary of this program? Summary first is that threads start concurrently. Lock ensures only one account operation at a time. Withdrawal waits if the balance is low. Deposit signals waiting threads. Interest calculation runs safely and the logging runs independently. Why this code is robust? Because it uses re-entrant lock. It provides benefit of re-entrant lock. It provides the fine-grained control. Then fair locking mechanism is used here that prevents the starvation, and we are having a condition which is used for efficient waiting, and thread pool is there that benefit of the thread pool is resource efficiency, and the while loop avoids these spurious wake ups. Why this design is effective? Because re-entrant log leads to fine-grained control, condition leads to efficient waiting, executor service provides thread reuse, separation of concerns provides scalable design. So this is the part solution to the part A of this case-based scenario problem. Then we are having the B part, that is evaluate the choice of synchronization mechanisms used. So chosen mechanisms may be re-entrant lock, condition variables, thread pool via executor service. As I have said earlier, re-entrant lock provides better control than the synchronized mechanism. Fair lock prevents the starvation, and fair lock can be evaluated using threads served in FIFO order. Condition is used because wait due to wait or notify altern because condition represents wait or notify alternative, and it is more flexible and readable. Executor service is used for thread management, and efficient resource utilization is provided. So why not only synchronized? Why not? There is a question. Why not only synchronized? So because uh, less flexible situation, maybe there no fairness control. It cannot interrupt log waiting easily. And now we'll be solving C part. Critically analyze how deadlock, starvation, and race conditions can be prevented. So race conditions. What is the risk of race conditions? Multiple threads modifying balance simultaneously. And the race conditions can be prevented by locking all the critical sections. Race conditions can also be prevented using while instead of if statement during waiting. And it can also be racing conditions can also be prevented by encapsulating shared data. Then deadlock. The risk of what is the risk of deadlock? Due to deadlock, threads waiting indefinitely for each other. There are several causes of deadlock. For example, multiple locks, circular wait, improper lock ordering. These are all the causes of deadlock. And deadlock can be prevented using single lock per resource. Deadlock can be prevented by maintaining consistent lock ordering. Deadlock can also be prevented by using try-lock with timeout. Deadlock can also be prevented by avoiding nested locks. Then we come to starvation. What is the risk of starvation? Starvation means low priority threads never execute. There may be several causes of starvation. Because, for example, unfair locking may lead to starvation. Excessive notify may lead to starvation. Thread priority misuse may lead to starvation. But starvation can be prevented by using fair locks. Starvation can be prevented by preferring signal all over signal method. Starvation may also be prevented by keeping critical sections short. And starvation may also be prevented by avoiding thread priority dependency. So we can compare all these three issues one by one. That is race condition, deadlock, and starvation. Race condition may lead to inconsistent data, and with the mutual exclusion technique, race condition can be prevented. Deadlock means circular waiting, as I have told you earlier. That is, threads may wait indefinitely for each other, and deadlock can be prevented by lock ordering. Starvation uh, leads to unfair access, but it can be prevented by fair scheduling. So now we reach to the conclusion. Proper synchronization is essential in banking systems. Advanced constructs like reentrant low condition executor service provide scalability, fairness, safety, and hence preventing concurrency issues requires design discipline, not just keywords. So we have now solved the case-based scenario problem, which may be asked in your end-term examination of 14 marks. Thank you for watching this lecture. Please like, share, and subscribe for more Java programming content. See you in the next session.